guys, we're in the physics lab, and this is my best partner in the world, Caroline. She can introduce herself in sign language. Oh, there you go. That was amazing. So at this class, I'll learn how to... Hey guys, this is the short version of my previous video, Physics of Juggling. In my last video, I discussed the theory of Josh Kaufman.
He says that in order to acquire a new skill and be relatively good at it, one needs only
20 hours. So
I decided to conduct an experiment and try to learn how to juggle.
Once again.
During my learning process, I was investigating the physics of juggling and also did some calculations. Okay, so let's get started. To collect data, I'm using Pascal Capstone software and sensors like video sensor, force plates, and goniometers. They will allow me to create graphs and extrapolate data from them. But first, let's talk about the representation of the magnitude and direction of forces. To do that, we use vectors. Magnitude is expressed by a numerical value. Direction can be represented in a variety of ways. We use quantitative, which is with coordinates or angles. So we'll analyze the movement as two-dimensional. Basically, we'll have x and y system of coordinate. For position, velocity, we have x and y, and acceleration, also x and y. These were my predictions for the linear world. I made a mistake here with velocity for x coordinate direction. What do you think, guys? Do you know how it should be? And also predictions for angular world. That's how my graph looked like. And these are the segments. You can pause at any time if you want. So at segment A, nothing is happening. At segment B, velocity in y direction going down, speeding up. In x direction, constant. Segment C, in y direction, the object is slowing down. In x direction, constant. In segment D, in y direction, we see speeding up, going up. In x direction, it's speeding up and moving to the right. Segment E, the object is in a free fall and only influenced by the force of gravity, so it reaches the turnaround point and starting to speed up, going down. In x-axis, object is moving to the right and has the constant speed. Segment F, in y direction, slowing down, going down. Also slowing down, going down, right. And the cycle starts again just to the left. Although I didn't have to do it, I still calculated the resultant vector. So at the point where ball leaves the hand, it is 3 degrees. Here I have force diagrams for each segment. Arrows represent the direction and relative sizes of forces acting on the ball. Green arrow indicates force of gravity. Pink arrow indicates force of the hand. Here I'm calculating the total force that is acting on a ball. I'm not gonna go into any details in this video. What happened here is that I picked 2 points on acceleration graph and calculated the total force. And here the total force is represented by black arrow. I also picked another 2 points and did calculations again, but this is a short version of the original video, so let's move on. Here I determined the segments at which object is gaining or losing the kinetic energy in x direction. And here is the same thing in y direction. Here is another graph. It gives us information about the change in kinetic energy in both direction and also the total change. This will help me to calculate how much power is generated during the throw, and which gives a half of the watt. Here is the net force over time graph. It tells us the average net force and change in momentum in both x and y directions. Okay, so now we are in the angular world and we'll do some calculations here, but first we'll start with segments. We are interested in the elbow and muscles, biceps and triceps. They will perform flexion and extension respectively. So here, angular position, velocity and acceleration helps us to determine which one is dominating at which segment. Here I'm calculating muscle forces according to my data. First biceps, and also triceps. I calculated as well how many calories I spent per single throw. So I took data from 3 sources and found that I spent approximately 2 calories per juggling session every day when I was learning how to do it. And finally, the Shannon-Claude's equation, where F is the time that ball spends in the air, D is the time that the ball spends in the hand, V is the time that hand is empty without the ball, N is the number of balls, and H is the number of hands. The closer the number I get, the better the juggler I am.
So this was the review of my video project. Hope it wasn't too boring for you guys. Peace.